Now let's look at what's known as QAM. First one is QPSK. And I think the interesting part of this is, and all of this, by the way, is not just because I want to teach you some basics, is all of this is just trying to in detail explain why does signal to noise increase throughput. And by application, why does a better signal, a much better signal, improve the amount of data you can send? So you can see here we've got a sort of noise that will be suitable for this. This is called decision boundaries. Okay, so you want to keep everything within this decision boundary, and it will be detected as this. So dot is a little bit big. We need to keep the boundaries or the area big. If we get 6 dB roughly better signal, we can put in, instead of 4, we can go put in 16, twice the number of states for that symbol. And once again, note the reason we can do it is now the boundaries are smaller. In other words, the areas which will represent the different symbols. And that allows us to do that, so we need better signal to noise. We can't try and fit those in because they will overlap and you won't be able to do it. But what we've achieved, we're still running at 10 megasymbols per second. You can see, and I just want to re-emphasize this because there is some confusion on this. If you now put all the possible combinations of 4 bits, okay, you can see that with 16, we can send 4 bits. So 2 to the 4 is equal to 16, hence 4 bits, not 16 bits. Okay, so now we can do 4 bits per symbol, okay, with a considerably higher signal to noise ratio. 4 bits per symbol means that we still got 10 megasymbols per second, but now we can send 40 megabits per second. Okay, so, and that's the same. I mean, I'm using the same resource of the base station. Base station can do 10 megasymbols dictated by bandwidth, which is a natural resource and is scarce, as we all know. As we increase it more, but note, that's quite an increase. I have to quadruple the signal, 6 dBs twice and twice, and I make the dot smaller. And in this case, I can fit in 64 different states, and 64 different states is 2 to the 6, so it will give you 6 bits per symbol. And hence, we are now treating nature quite nicely, okay? We're going now at 60 megabits per second, still using just 10 megasymbols. And lastly, 256, not lastly, this is currently, most probably, I think the newest release of LTE would go one step more. And here I can go 8 bits per symbol. Okay, so now I can send 80 megabits. But please just note, this is fantastic. We've done a lot of technology here, and we've gone up to 80 megabits per symbol in a 10 megasymbol channel, but we pay for that. In other words, the cost of this is receiving a signal, and if you take 2 times, 4 times, this is 8 times, 16 times, 32 times 16. We had to increase the signal by 80 dB, almost roughly 100 times to what we needed to do this. Now, when a radio communicates with a base station, it will see, is the signal strong enough? Then it will do this. Okay, so it can send a lot of data to this guy per symbol. The signal is weak, it has to downrate and figure out what works. And to this guy, also using the same symbols, it can send much less data. I think this already starts giving everyone an idea of why it is such a severe impact on capacity. Or in other words, the signal or the average signal to noise that your users get impact the base station's capacity, because that base station just now doesn't have more channels or anything. It's got that 10 megasymbols in a cell per second. That 10 megasymbols must serve everyone in that cell. And if some guy wants to use many megasymbols in order to send a little bit of data, it obviously reduces the capacity of that cell.